Thank you for that very nice introduction, Allison, and hello, everyone. So, the goal for those of us who are participating in the Massive Stars workshop here this week, Cosmic Change Agents, is to understand the nature of massive stars in the early universe. And today, I will provide some context for why this is an interesting and timely problem, and also for why it's a really challenging problem that warrants a 3-week Aspen workshop, right? So my own research program uses observations of very nearby galaxies that we see at the present day to shed light on how stellar physics changes in the early universe. And my goal is that by the end of my introduction, you will all understand why this is a useful thing to do. So since not everyone here is an astronomer, I just want to start with kind of an overview of massive stars and why we all care so much about them. So stars that are more than about 20 times more massive than our sun are found at the top of the Hertzsprung-Russell diagram. So this is the luminosity of a star plotted at the function of its surface temperature. And these stars can be more than 1 million times more massive than our sun. And this really intense radiation that they produce can drive outflows of material from the stellar surface. So they drive radiation-driven stellar winds. The stars also have extremely short lifetimes. They live for something like 10 million years or less. For context, that is less than 1,000 times shorter than the lifetime of our sun. And their lives often end very dramatically as supernova explosions, okay? So when massive stars are in the longest phase of their lives, when they're burning hydrogen into helium in their cores, they live on what we call the main sequence in the Hertzsprung-Russell diagram, basically ordered by mass. But again, they're up here at the top and all the way to the left of the plot because these stars are very hot. And we call them O-type or O stars, and you'll see that term throughout my talk. These O stars are so hot and luminous, in fact, that they dominate the production of ionizing radiation in their host galaxy. And by ionizing radiation, I mean photons that are energetic enough to ionize a hydrogen atom. So I've flagged many processes in this list with an asterisk here because these are all forms of what we call stellar feedback. And these are all ways that massive stars impact their galactic environment. So stellar feedback is deposited into the gas surrounding a star-forming region on very local scales, right? So we see these little pockets where star formation is happening. Again, stellar feedback includes processes like radiation pressure, mechanical energy from the stellar winds, and of course, supernova explosions. And in addition to all of that energy that's being dumped into the gas around these star-forming regions, massive stars also dominate the production of heavy elements in galaxies. So these are called nodes. Is the microphone okay? It's cutting in and out. That's not ideal. Okay. We'll see. I guess I'll let the AV expert decide if we need to intervene. So astronomers call every atom that is heavier than helium a metal, which is obviously not correct, but that is the jargon, and that's the term I'm going to use through the talk. So now it's been defined, and we're all on the same page. By the way, I am doing my best to introduce all the necessary concepts and terms, but if you have clarifying questions, please just raise your hand and ask me. Okay, so all metals are returned from stars into the gas through either the stellar winds themselves or when the stars end their lives as supernova explosions. And when star formation is very intense, the collective impact of all of this stellar feedback can drive these large-scale outflows of metal-enriched gas out of the host galaxy. And this will regulate, how many stars can form and what the chemical composition of subsequent generations of stars will be in that galaxy. When these outflows happen, basically, channels are carved in the dense gas through which ionizing photons that are produced by the massive stars can escape from the host galaxies and actually reach out into what we call the intergalactic medium. So this is the diffuse gas that fills the space in between galaxies. So the point of all this is that massive stars are super important, okay? They have substantial impacts on the evolution of their host galaxies and of the evolution of the universe more broadly. So one of the lofty goals in astrophysics that was outlined in the 2020 Decadal Survey is to form a complete understanding of how all this works. We produce the galaxy populations that we actually observe at different epochs in cosmic time. So in the last few years, astronomers have gained a fantastic new tool to directly observe the early stages of galaxy evolution, called the James Webb Space Telescope, or JWST. So as we heard from John Chisholm in his colloquium last week, for those of you who were here, we observe galaxies that are very far away from us. And when we do this, because of the finite speed of light, we are also looking back in time. So we're seeing these galaxies as they were in the very distant past. And as light from very distant galaxies travels toward us, the cosmological expansion of the universe actually stretches the wavelength of light emitted from those galaxies. So when a galaxy emits ultraviolet and visible radiation, it becomes redshifted to longer wavelengths. We observe it in the infrared, and that is exactly where JWST operates. That makes us very sensitive now to these early distant galaxies, which we call high redshift, because again, their light has been shifted to redder wavelengths. So here, I'm showing you one of the very first JWST observations that was released to the public in a splashy press release back in July of 2022. I'm showing you this for two reasons. First, I want you to note this picture of a galaxy that is seen about 1 billion years after the Big Bang. It's a blob, right? We are not getting a lot of detailed spatial information about these very distant and early galaxies. So essentially, we are measuring their integrated light. Even in very high resolution imaging from JWST, you can see lots of detail in the bigger image, and this is a zoom into a tiny part of it. Second point is that the bottom panel here shows the light broken down as a function of wavelengths. So this is a spectrum. And you see emission lines of individual ions that are emitted at known rest wavelengths. So this kind of data, which we can now get for galaxies very early on in the universe, this is truly transformative, and it gives us the ability to measure gas conditions in these early galaxies, including their metal abundances. So despite this amazing new information we have about early galaxies, thanks to JWST, we're still left with quite a number of open questions, and some of these have been raised by JWST observations in just its first few years. So to give a few examples, these emission line spectra that we observe in high redshift galaxies require very intense and energetic ionizing radiation to produce them. This must be a source unlike anything that we see in very nearby galaxies, and this remains kind of a puzzle for us. Related to this, we know that in the early universe, intergalactic medium, the gas in between galaxies, must have transitioned from being neutral to ionized. We don't know yet which galaxies were the dominant source of those ionizing photons. So was it a lot of small galaxies or just a few very massive galaxies that dominated that process? Finally, again, these emission line spectra have showed us that many early galaxies have very quickly become very enriched in nitrogen and have other odd chemical abundance patterns relative to what we see in the local universe that are very difficult to explain with our current understanding of nucleosynthesis. So to answer all of these questions I have just laid out for you, we really need to understand the sources of ionizing radiation and new heavy elements in these early galaxies. And a very likely culprit here is the massive stars. So more broadly than that, if we want to measure some physical property of a galaxy that we observe, say I want to know the age of its stellar population, or the total ionizing spectrum that is emitted by its stellar population, then I need to construct a model of that galaxy's light using various types of stellar models as inputs, okay? So first, we need to know the initial mass function. This is the number of stars formed per mass. And I mentioned early on that massive stars are rare compared to low mass stars, and so the IMF typically decreases toward high masses. Another important parameter in this IMF is the most massive star that you form. The luminosity and ionizing radiation production of a massive star is a very steep function of its mass, and so that actually turns out to be a very important quantity that we do not actually know very well, or how it evolves with cosmic time. We also need models of stellar evolution, which describe how a star's properties change over its lifetime. So here I'm showing tracks of stars of different initial masses through the Hertzsprung-Russell diagram. So again, that luminosity temperature plane. And finally, we need template stellar spectra. Basically, we need to be able to say, if I were to observe a star at this point on its evolutionary track, what spectrum would I observe? And be able to map these template spectra onto the evolution models. So putting all of these together, we can create what are called simple stellar population models, where you have the flux as a function of wavelength that you predict to be emitted in total by a stellar population spanning all the different masses that was formed at a particular time. And then you have SSPs, simple stellar populations of different ages. So what I want you to notice in this figure is that for young ages, basically any galaxy that is still actively forming stars will fall into this category, and this includes basically most galaxies that we're observing these emission line spectra for in the early universe. This light is dominated by massive stars in the UV and optical wavelengths that we're observing with JWST. So we absolutely need good models of massive stars if we want to interpret observations of early galaxies. Now, these various kinds of stellar models all need to be calibrated against observations of individual stars. And this is really only possible to do in the local universe, galaxies that are very close to us. To see why, let's go back to that image from my title slide.
Question?
Yes.
What does the local universe mean? Universe is in?
Yes, that's right. It's a very squishy term. It depends who you ask. For this talk, I mean within a couple of megaparsecs. There are different definitions, though. People will refer to the local volume as within, megaparsec. Thank you. Okay, so a parsec is 3 light years, so it's something like 6 million light years of us, okay? Different people will say different things. The local volume is a much larger entity, out to something like 20 megaparsecs. It just depends on the community that you're talking about. But here, we are massive star spectroscopists. You can't do stellar spectroscopy beyond about 2 megaparsecs from here. So that's my definition. Any other clarifying questions right now? Okay, great. So this galaxy is called Leo P. It's 1.6 megaparsecs away from us. And this is a JWST NIRCam image where the exquisite spatial resolution of this instrument can pick out all of the individual stars in this galaxy. So all of these blue points of light that you see are stars in Leo P. Now, let's zoom in on one of these background galaxies that we see in this image behind Leo P, okay? This is a very different kind of observation. You cannot pick out individual stars in this galaxy, and all of its light is blended together. So for these more distant galaxies, we can't analyze individual stars. We are really restricted to measuring integrated light, either over regions within the galaxy or from the entire galaxy that we observe. And honestly, that background galaxy is not even that far away from us. It gets way harder when you go to the earlier universe. We really do have to stick to a handful of very nearby galaxies if we want to measure individual massive stars. But there's still a missing puzzle piece here, right? How can I possibly use nearby galaxies that are observed at the present day to say anything about the physics that was operating in high redshift early galaxies, right? Well, for me, the key connection is galaxies' chemistry, or metallicity, right? Metallicity is defined as the abundance of heavy elements, metals, relative to hydrogen. And so the figure I'm showing you here, the metallicity of a galaxy is a function of its total stellar mass. So this is all of the mass in that galaxy, not the mass of an individual star. And you see this observed trend between the two quantities in the local universe. This is basically related to the fact that stellar feedback is more efficient at removing gas and metals from lower mass galaxies, because they have shallower gravitational potential wells, and so they don't hang on to their material as well as more massive galaxies. Now, if we look toward earlier cosmic epochs or higher redshifts, we see that at a fixed stellar mass, metallicity is lower for galaxies across cosmic time. So again, this is basically because there have been fewer generations of massive stars synthesizing new heavy elements, but there's of course a complex interplay of physical processes there. But the implication of these empirical correlations is that in the local universe, we can go down to very low stellar mass galaxies and probe metallicities that are typical, sort of more normal galaxies at higher masses in the early universe. Okay, so that is the kind of work I am going to present today. So in the first part of the talk, I will show you some observations of individual massive stars in nearby and low mass galaxies and what they can teach us about stellar astrophysics at low metallicity. And I'm going to focus on one aspect of massive stars, which very strongly affects models of massive star evolution and ionizing photon production. And that is the stellar mass loss rate via radiation-driven winds. So that's the quantity on the y-axis here. And how it depends on various stellar properties, like the stellar luminosity on the x-axis. So as I mentioned earlier, the energetic radiation from these stars transfers momentum to the outer layers of the atmosphere to drive outflows away from the stellar surface. This momentum transfer is mediated by metal line transitions, and so it's theoretically expected that low metallicity stars should drive weaker stellar winds. But the point of the figure I'm showing you here is that when you go to low metallicities especially, here I'm showing you 20% of the solar value, which is typical of our Milky Way, different theoretical mass loss rate prescriptions are pretty discrepant, right? So this is a problem for us. We need to get the mass loss rate right because it affects not only a star's predicted evolutionary pathway and how it should end its life, but it also affects the amount and hardness of ionizing radiation that can escape from the star's atmosphere. So the figure on the right here now shows several theoretical O-star spectra that were calculated from an atmosphere model. And the key difference between the orange line there and the rest is that it has a much higher mass loss rate. So this dense stellar wind is driven by absorbing more energetic photons, like those that are capable of producing some of the extreme nebular emission lines that we're now seeing a lot of in the early universe. So again, we really do need to understand mass loss rates if we want to understand massive stars in the early universe, and what we really need is empirical measurements of mass loss rates from individual low metallicity stars. Fortunately, stellar winds do produce observable signatures. And the most useful of these are found in the far ultraviolet part of a star's spectrum. So in this cartoon, we have a star driving its radiation-driven wind in the radial direction, and it produces isotropic emission, right? And so that will produce a profile that looks like this, centered on 0 velocity at the center of the emitted metal line. You will see emission both in negative velocities, where the material is moving toward the observer, and at positive velocities, where the material is moving away. But along the line of sight from the observer to the star, you'll also get absorption because the material is backlit by the star itself. You'll only see that absorption in the blue shifted direction. And so when you sum these two contributions, you get this very characteristic wind profile. We call this a P Cygni profile, named after a star called P Cygni that has very prominent stellar wind lines. So these P Cygni profiles in the far UV can really only be observed with the Hubble Space Telescope. Because unlike JWST, Hubble can access these UV wavelengths, and you'll see Hubble features very heavily throughout this talk. Just want to emphasize for the non-astronomers, Hubble has very much not been replaced by JWST. I get this a lot from my friends. No, Hubble is still going strong, and it's very important that we still have Hubble because JWST and HST are very complementary. They probe different parts of the spectra of massive stars and galaxies and what have you. Okay, so using the Hubble Space Telescope, best laboratories for low-metallicity stellar astrophysics are these very nearby galaxies called the Magellanic Clouds. So the LMC and SMC are the large and small Magellanic Clouds, and they have metallicities of 50% and 20% of the solar value. Even in these very nearby galaxies to us, though, high-quality stellar spectroscopy was pretty limited until a recent major effort by the Hubble Space Telescope Ulysses program, which assembled ultraviolet spectra of over 250 massive stars in these galaxies. So you'll see the familiar O-type stars up there. There are also B-types, which are basically the next most massive and luminous category after O-types. And the X-shooting Ulysses program was a community-led follow-up effort to get optical spectroscopy of all the targets in the Ulysses program. This was using the Very Large Telescope in Chile. And I'll explain this more a bit later in the talk, but we need both UV and optical spectroscopy if we want to do quantitative analyses of these stars and their winds. So I want to highlight many active members in this XShootU collaboration are here in this room. My sincere apologies if I have missed your name, but want to call out that there is a wealth of expertise in this area right here at Aspen this week. Okay. So these fantastic new data sets, members of the XShootU collaboration have put out a series of papers characterizing the stellar winds for very large numbers of metal-poor massive stars, including terminal wind velocities here that were measured by Callum Hawcroft, who's right over there, and mass loss rates and the strengths of the stellar winds, which are quantified by this modified wind momentum. That's what's plotted on the y-axis here. You see, we have these quantities now broken down by galaxies, so you see actual differences across the LMC and SMC. So we're probing the changes as a function of metallicity when we go below solar. This is a huge improvement over the situation even just a few years ago. But again, Ulysses only gets us down to 20% of the solar metallicity. We're now routinely observing more metal-poor galaxies than this in the high redshift universe. There are a handful of more metal-poor O-type stars in the bridge of gas that actually connects these two galaxies, but there's only a few that we know about. They've actually been analyzed by Elisa Schlosser, who is in Andrea Sanders' group at Heidelberg. But to find a larger population of these lower metallicity O-type stars, we need to look in galaxies that are quite a bit more distant than the Magellanic Clouds. This means that individual stars get very faint because flux falls off as 1 over distance squared. So historically, these expensive observations have not really been done. So we do lack an empirical observational data set for massive stars at these very low metallicities. We can do these observations with our current generation of telescopes if we invest a lot of time in the problem. So this is what I have been spending a lot of my effort on in recent years, is working to fill this gap, starting with a pilot of 3 O-stars in these 3 nearby low-mass galaxies that span 3 to 14% of the solar metallicity. So our team observed far UV spectra of these stars using the COS instrument on Hubble, which again gives us access to these key diagnostics of radiation-driven stellar winds. Here, I'm showing the COS spectra that are zoomed in onto 2 metal resonance transitions. So we have a nitrogen 5 line, well, doublet on the left, and a carbon 4 doublet on the right. And just by eye, we see that these low metallicity stars don't have those full-blown P Cygni profiles I was showing you in the cartoon a few slides ago. So we know that these stars have to be driving quite weak stellar winds. But to actually quantify that requires more data. As I mentioned before, to do a quantitative analysis requires both UV and optical spectroscopy. So I went back and observed these stars with the Keck Cosmic Web Imager, which is a spectrograph on the ground-based 10-meter Keck telescope in Hawaii. And I did this so that I could measure the strengths of helium lines in the optical part of the spectrum. The different ionization states of helium give us a measure of the star's temperature, and the shapes of these hydrogen Balmer absorption features give us a measure of the surface gravity of the star, or basically how dense it is. And you can't really measure those 2 quantities robustly from far UV spectra alone. So, the observed spectra are shown in black in these 2 panels here. And the red shows a new atmosphere model that I ran using the power code in close collaboration with Andreas, John, and Danielle, who are all in this room. And we tailored these new atmosphere models to simultaneously reproduce all of the stellar and wind diagnostic features that we have in both the UV and optical spectra. And from the best models that we fit to the data, we can then infer all of the stellar and wind properties that we're interested in, and can finally compare measurements of their mass loss rates to predictions at these very low metallicities. So this plot is showing the mass loss rate as a function of the star's luminosity. My new measurements are these black outlined circles with error bars. And the colors here indicate the best iron abundance in our preferred model for each of the 3 stars. And for comparison, the lines and the squares here are all showing 3 different predictions for how mass loss rate should vary as a function of metallicity and luminosity. So overall, the take-home point here is these new mass loss rate measurements agree best with the low end of the wide range of model predictions on this plot. Again, we need to know if the mass loss rates are low and include these in stellar models, because they do affect how a star will evolve over its lifetime and how much ionizing radiation will be deposited into its surroundings. It'll also affect the predicted far ultraviolet spectrum of these stars and of, integrated stellar populations. So most of the widely used models that go into the kind of galaxy light models that I was describing in my introduction typically adopt a classic mass loss rate prediction from Bink et al. 2001. So that's the squares here. And you'll notice on that log-scaled plot, those predictions are something like an order of magnitude higher than what we are inferring from these new observations. This is really not a subtle difference either. To drive that point home, this figure illustrates, again, my best fit model in red compared to the data in black behind it. And for comparison, the blue model shows what happens when I take the predicted mass loss rates for the best fit properties of that star and change that mass loss rate in the power model. I keep everything else the same, and you get this really dramatic P Cygni profile. This is obviously inconsistent with what we are observing, and I think this is important to get right in the spectral models, especially we're using to interpret high redshift galaxy observations. Because even with JWST, We are really only probing the UV and optical parts of the spectra, right? And so these stellar wind features become valuable stellar population property diagnostics at high redshift. Yes.
Yeah, I mean, it's hard to tell because there are no error bars, but looks to me that even the best fit data from the power model is not a really good fit.
Sure, yeah, it's not a perfect fit by any means. We are operating at a very low signal-to-noise regime here for the standards of stellar spectroscopy. This is the fundamental trade-off you make when you push out to these very large distances. So rather than let every possible parameter in the power models be free, we make some simplifying assumptions and adopt sort of standard prescriptions. So, for example, perhaps you were looking at these nitrogen lines in the power model, right? That peak could probably be adjusted, but I wouldn't necessarily believe the best fit value of the parameter that we would infer by making that adjustment, and it doesn't really change the mass loss rate parameter that we do care a lot about. So yes, it's not a perfect fit. If you look at similar papers in the literature, you'll see the power models or whatever other atmosphere modeling code, you often don't get an exact match. This is pretty good. Yeah, great question. Anything else? Okay. Great. The point is at profile, very clearly inconsistent with what we observe. Okay. So I've been focusing on a sample of just 3 stars, right? And I also have, these other 3 stars that were analyzed by a different team back in 2015 on this plot. This is not a lot of data. Clearly, a larger sample would be very helpful here. So we don't have a really densely sampled Ulysses-style data set at these lower metallicities. And to illustrate what we do have available to us, I'm going to populate this parameter space plot where I'm showing the luminosity class of a star, which is basically how evolved that star is away from the main sequence. And I'll show that as a function of spectral type, or basically how hot the star is. So to orient you, more massive stars will start their lives over to the left on this plot. Typically, stars will evolve upward and to the right over their lifetimes. As of 2024, we had far UV spectra of high enough quality to do the kinds of measurements I've been describing for 17 O stars in these nearby galaxies below 20% solar metallicity. You can see that they all occupy a very particular region of this parameter space, right? So we're missing the massive stars, which would lie over here, which would also be the hottest and dominate the ionizing photon production of that stellar population. We are also missing the latest type and lowest mass O stars. So these, again, they're more common than more massive O stars, and they're also very common progenitors of supernova explosions. And they're not really represented in our existing data set. So, remedy that situation, I am leading this Hubble Space Telescope Treasury program called TEMPOS, the Treasury of Extremely Metal Poor O Stars. And this is work done in collaboration, again, with many wonderful people, including several workshop attendees who are here today. And right now, we are observing a dozen more stars to complement the existing archival spectra and really fill out this parameter space as much as we can. And this is the best we can do given our current technological capabilities, so basically what Hubble can actually reach, and given our current knowledge of the O-star content of these nearby low metallicity galaxies. To highlight these 3 circled stars here, these were recently identified as O-types in my own ground-based observations of these nearby galaxies. So we do not, by any means, have a complete inventory of O-stars in the local universe. Okay, and as I explained before, you need both UV and optical spectroscopy to analyze these stars in detail. We also got Keck optical spectroscopy of all of the targets and tempos spread across these different galaxies. And this is exactly the kind of data set that we need to calibrate models of stellar mass loss, evolution, and ionizing spectra. Very excitingly, we did finish collecting the Keck data in January. After some run-ins with bad weather, we finally got everything that we needed to complete the program. And Christy Erba, who again is in this room, is now leading the reduction and analysis of much of this optical spectroscopy. Okay. Now, to show you what we can do with those optical spectra, let's look at the first of these data sets I collected in the galaxy NGC 3109, which has now been analyzed by Abby Mintz, who is a PhD student who worked with me at Princeton. And this figure is showing how that Hertzsprung-Russell diagram in this low-metallicity galaxy was populated before we went back and did these DEIMOS observations with Keck. Abby's modeling of those new optical spectra has really filled out the Hertzsprung-Russell diagram here and has nearly doubled the number of well-characterized O-type stars we know of in this galaxy. On top of that, we found a surprise in this data set. There was one star that had actually been previously classified as a relatively cool, evolved O-star, which turned out to be quite hot, something like 45,000 Kelvin. And it might actually be the most massive star that we've yet found in one of these low metallicity nearby dwarf galaxies. But we have very few examples of very hot stars like this, which again are expected to dominate the ionizing photon production of their stellar populations. So this discovery really emphasizes that things like this could still be out there waiting to be found, and we should really keep looking for them. Okay. So to summarize the first part of the talk, I've shown you evidence for very weak winds in O-stars at low metallicity. I've argued that this is an important thing to account for in stellar evolution and spectral models. And with data from Ulysses and X-Shoot-U, as well as the ongoing TEMPOS program, we'll really be able to rigorously calibrate stellar models that are appropriate for interpreting observations of metal-poor galaxies, especially those in the early universe. Okay, in the second part, we're going to focus on how massive stars form in the first place, these very low metallicity galaxies. And I'm also going to highlight an example of how JWST is transforming our ability to observe nearby galaxies, as well as galaxies in the early universe, by giving us access to the rest frame infrared light. I already mentioned way back in my introduction that stellar feedback can drive gas out of galaxies, right? That's only part of the story. This is a figure illustrating what we call the cosmic baryon cycle. So gas can actually cool and accrete onto a galaxy, whether it's been in the galaxy before or if it's freshly accreted from the intergalactic medium. Then, once inside the galaxy, gas can cool further and collapse to form new stars. Now, observationally, we see that star formation happens in cold, dense clouds of molecular gas. These are dominated by molecular hydrogen, or H2, in terms of their mass. When we see this, we are typically looking in relatively metal-rich galaxies, so like our Milky Way or maybe a bit more metal-poor. In the very low metallicity regime, the situation is actually expected to be quite different. Essentially, the chemistry and cooling of low metallicity gas changes enough that the timescales for H2 formation become much longer, okay? And simulations of the interstellar medium, meaning all of the different phases of gas that are present in a galaxy, predict that at very low metallicities, star formation can actually occur in gas that is mostly atomic before molecular hydrogen has a chance to form. And we need to understand if this very different mode of star formation really does occur in metal-poor galaxies, particularly those in the early universe, because this has implications for the timescale of star formation, right? So when we would expect massive stars to form and start depositing feedback and ionizing radiation into the intergalactic medium, right? All of these timescales depend on our model of star formation. So, clearly, we need to go look at some nearby low-metallicity galaxies and see if they have molecular gas, right? If only it were that simple. So, turns out that molecular clouds, again, are dominated by H2 in terms of their mass, but cold H2 in star-forming clouds does not emit any detectable radiation. So, we have to use tracer molecules to identify clouds of molecular gas. By far, the most common tracer is carbon monoxide, or CO. So in metal-rich galaxies, we see that there are large, cores of carbon monoxide at the centers of these cold molecular clouds, and they're very bright in CO emission and very easily detected. This is a great tracer particle. At low metallicity, the structure of molecular clouds changes. Basically, metal-poor gas is less good at shielding the cores from ultraviolet radiation, which dissociates carbon monoxide very easily. So CO cores become tiny. There is a little core right in the middle of that cartoon, but it's not very luminous and really, really becomes challenging to detect. But we can certainly go observe low metallicity galaxies and give it a shot, right? So to do this, we're going to return to that galaxy I showed on my title slide. This is Leo P, again, just a 3% solar metallicity galaxy. It is by far the closest galaxy to us that is this metal poor and still forming stars. And interestingly, it has only one known O-type star that dominates the production of ultraviolet and ionizing radiation in this galaxy. So this is an unusually simple situation, and it makes Leo P a really useful test bed for models of star formation and the interstellar medium in metal-poor galaxies. So, carbon monoxide has been detected after many years of efforts in low metallicity galaxies in the nearby universe, but it does remain elusive at the very low metallicity 3% solar of Leo P. Our team actually did a deep observation with ALMA, which is one of the premier ground-based telescopes that's capable of detecting CO emission at millimeter wavelengths. This is in the Atacama Desert in Chile, but we found nothing. Like I said, it's still possible that there's a lot of molecular gas in a low metallicity galaxy like Leo P, even if we cannot detect CO. So to test that possibility, I led a JWST proposal to search for an alternative observational tracer of molecular gas, which is rotationally excited infrared emission from molecular hydrogen that's excited by ultraviolet radiation from that O-star. We actually did detect a line from a molecular hydrogen molecule in Leo P. This is the first direct evidence of molecular gas in any star-forming region at such a low metallicity, and we see it right at the edge of this cloud of gas that's ionized by the O-star. This is exactly where we would expect a colder molecular gas phase to meet with this warmer gas and actually be exposed to ultraviolet radiation. This is basically exactly the picture that we had in mind when we designed the observation. This is great, but the molecular hydrogen emission that we observe in Leo P is very, very faint. We have one emission line securely detected, so it's definitely there. We only have upper limits on 2 other lines, and we would really like to have more information than this to pin down the temperature and column density and therefore mass of gas that is present in this warm H2 cloud. Yes?
Will the molecular cloud also absorb sources behind it? And if so, can't you see the lack of those sources, like of stars?
They're in what wavelength?
In whichever. I would think it's optically thick, and so you would not observe stars in optical light.
Oh, you're thinking it's dusty.
Yeah, something like that.
Very low metallicity galaxy. Basically, the only dust constraints we have right now in Leo P are from the H2 region, and it's consistent with 0 extinction. But again, the fact that we are seeing molecular gas strongly suggests that there's some dust there. There kind of has to be, otherwise you wouldn't forming molecular gas, again, because you need the dust to shield. Yeah. There's not enough dust to be easily detectable and observed.
Could you say what is the wavelength of the line you observe?
Yes.
This redshift that's...
So this is basically not redshifted. Think of it as redshift 0. The velocity of the galaxy is 260 kilometers per second, which is a tiny, tiny redshift. The wavelength of light is 17.1 microns. So this is done with the MIRI MRS spectrograph on JWST. Anything else? Okay. So we have upper limits on 2 of these lines. And while it doesn't let us measure or model the temperature of the gas, it does allow us to place some limits, okay? The lines on this plot are showing 2 possible scenarios. Either we are detecting a cold molecular gas clump that is at basically the lowest temperature that can produce detectable rotationally excited H2 emission. That would correspond to a column density that is consistent with what we observe from molecular clouds in the Milky Way galaxy. Alternatively, we could be looking at a much warmer molecular cloud, something like 400 Kelvin, model shown in red here. And that would, again, correspond to a mass that's orders of magnitude lower, which would be pretty different than what we see in the Milky Way galaxy. But remember, we know a lot about the O star's ultraviolet radiation from the work that I showed you in the first part of the talk, right? I've observed an ultraviolet spectrum of this O star. So we used that data in a model of the gas in Leo P and demonstrated that there's no way to get the temperature of this warm H2 phase up to the upper end of this formally allowed range. In fact, the modeling actually prefers a temperature that is very similar to the blue model that I'm showing here. So we're able to constrain the temperature and mass of this warm H2 in Leo P, this lower temperature and therefore higher mass end of the allowed range. And more than that, warm H2, what's detectable with JWST, this should really be a small fraction of the total molecular mass in the galaxy. There's very likely more colder H2 that is in Leo P, but is not detectable with JWST because it's not exposed to ultraviolet radiation. Yes.
Sorry for interrupting.
No, you're fine.
Could you say why don't you see the S0 line that starts from S1?
Oh, the sensitivity of MRS gets awful at the longer wavelengths where the S0 transition lies. It's at something like 25 micron, no, 28 maybe? I honestly don't remember because I couldn't analyze the line. It's just pure noise. There was no way to even get a useful limit on it, which is really a shame. So basically, increasing numbers of these S transitions, S1, S2, S3, these are probing hotter and hotter temperatures. And so S0 will be here at 510 Kelvin. We just don't have a limit on it. So.
And the S2 and S3 here, is it you see a spectrum but there's no line there, or is it that you're just seeing complete darkness, no photons?
You see noise, basically. So it's an upper limit. It's basically, you know, we can't rule out that there is emission there, but we can rule it out up to this sensitivity, right?
So it's not instrument noise, it's foregrounds or backgrounds.
So it kind of is the background, actually. Background subtraction is quite challenging, and this is a very faint target. So if you observe something really bright with this instrument, no problem, it's great. But we were going for something that we knew would be very, very faint, and it's still early days in JWST. People are actively working on the data reduction pipeline, and it's getting better all the time, but we are just noise limited here. It is the background and infrared that makes it hard. Okay. So, demonstrated that this very metal-poor galaxy has likely been able to form quite a lot of molecular gas. And this is, you know, a new and useful constraint for models of the chemistry and star formation happening in low-metallicity gas, and is particularly relevant for galaxies in the early universe. Okay. So to summarize, second part of the talk showed you how JWST is opening up new ways of studying star formation physics at very low metallicity. And I think LEO-P really nicely showcases the kinds of insights that we can get about the early universe from these detailed observations in very nearby and very low metallicity galaxies. Now, of course, there are important differences between these local galaxies and those in the early universe. And local galaxies will always be useful but imperfect analogs, right? So we really do need to combine this kind of knowledge with the new observations that are now being made at high redshift, especially with JWST. And that is exactly the reason that we have all convened here in Aspen. Okay, with that, I will leave up my conclusions and take more questions. Thank you.
Grace, thank you for a lovely talk. I had a question from the outsider. I've read that it's believed that in most galaxies there's a black hole at the center, there are black holes at the center, and yet you didn't discuss that at all here. Is there any interaction between your massive stars and these black holes, or do they play a role in the evolution in the development of these black holes?
It's a wonderful question. So yes, that is the picture. Galaxies do, in general, have supermassive black holes at their centers. There is basically what we call a scaling relation between the mass of the supermassive black hole and the mass of a galaxy, right? And so it's a power law. More massive galaxies have more massive black holes, typically. The situation gets tricky when you get down to low stellar mass galaxies because black holes start to get into a regime where it's more challenging to detect them. And in fact, they become small enough that we no longer call them supermassive black holes. We call them intermediate mass black holes. And that's a whole different enigmatic category. This is outside my area of expertise, right? I have been focusing on dwarf galaxies, and we don't think that black holes play a huge role in the evolution of dwarf galaxies. But there are people who are out there hunting for massive black holes in those kinds of galaxies, right? So don't rule it out, but that's the current state of affairs. At the massive end of galaxies, yes, supermassive black holes play a huge role. They, like stars, provide feedback and can clear gas out of the centers of galaxies. Yes, they're a very important part of galaxy evolution.
Thank you.
In the back, yeah.
So I'm not an astrophysicist, but more like a molecular spectroscopist. So I'm wondering what for this molecular gas in the star formation, what kind of temperatures is relevant for your study?
That again depends on the metallicity of the galaxy that you're talking about. For galaxies like the Milky Way, around solar metallicity, gas can get as cool as a few Kelvin, right? Less than 10 Kelvin in the cores of molecular clouds. At lower metallicity, again, the cooling physics is a little bit different, and so molecular clouds are thought to stay a bit warmer than that, like tens, maybe 100 Kelvin for star-forming gas, but that's pretty high.
Yeah, so for what kind of, like, on-Earth molecular spectroscopic measurement would be helpful for your observations?
Insofar as, need to know atomic data, or I guess molecular data in this case, right? We need to know precise oscillator strengths and transitions of wavelengths, or wavelengths of transitions. Like, yes, I think that is very useful. This is way outside my area of expertise, though. I look these things up in papers and I use them happily. So I would love to discuss with you more if you have something more specific in mind.
I guess it's the last very simple question. So when you talk about this very red-shifted observations, how do you get the reference? I mean, how do you know the spectrum at the rest frame? So.
Yeah, that's a good question. Basically, we see a very characteristic set of these emission lines in galaxies across cosmic time. And so there are basically some very clearly identifiable features that have characteristic spacings and wavelength from each other. And so it's fairly straightforward to pick out, like, oh, this is my oxygen 3 line that was emitted at 5,007 angstrom, right? So if you identify a few of those well-known emission lines, then you can pretty reliably measure how much your light has been projected. Thank you. Yes.
you look directly at H2, but earlier you mentioned that CO is used as a tracer.
Yes.
So for me as an outsider, it seems like there's quite a complex relation between H2 population and CO.
Yes.
There's a lot in between going on.
Yes.
Why is CO regarded as a good tracer?
Easy.
Yeah.
You can detect it.
Yeah, but I mean, there's a lot of chemistry on the way.
Yes.
And nuclear, stuff.
Yes, I think it's very messy. Basically, we use a very simplistic tool called the CO to H2 conversion factor. And you measure your CO luminosity. It's empirically determined. Honestly, this is a pretty new research area for me. I'm not a molecular gas or CO expert by any means, but my impression is that, Milky Way metallicity, solar metallicity, you can pretty much believe it. But when you go down to low metallicities, like what I'm talking about in LEO P, the conversion factor is completely unknown, and people predict orders of magnitude different values for it. So it's just wildly unconstrained. In this case, yes. And we are trying to go back and get deeper CO observations to try to place a useful limit and actually be able to say something interesting about how big that CO to H2 conversion factor might be. We'll see. Yes.
I have a very pedestrian question. What about those early galaxies discovered by JPST, which are maybe contradicting the Big Bang theory, and does your research shed any light on that?
We heard about this from John last week, actually. My research does not really shed light on this, but I think the general picture is that the assumptions that you make in the kinds of models of galaxy light that I was talking about back in my introduction, the assumptions matter a lot. People were basically making some simplistic assumptions that led to very, very high masses of stars needing to be formed very early in the universe. And later generations of slightly more careful modeling maybe solved the issue. So don't worry, we have not broken the universe. All's well.
So our universe is not cyclic?
Don't think so. We're all good. Yes.
So you didn't talk about the Milky Way.
Correct.
So is it that it's just an old galaxy, metallicity is too high, there's some rare pristine neighborhood where nothing happened until recently, and there's a low metallicity star in our galaxy?
No, I asked this question, I think, to Paul not too long ago. I asked if there are any of these, massive O-type stars that are way out in the outskirts of the Milky Way where we do expect, we see that the metallicity is lower, right? Spiral galaxies like the Milky Way have metallicity gradients, so they're more metal rich in the center and typically fall off toward the outskirts. But basically, there are no ionizing O-type stars that we know of in those more metal poor outer parts of the Milky Way. There are some B stars. They don't produce a lot of ionizing radiation, and so for my particular research program,
Okay, one last question and then we'll break.
Atomic hydrogen. Do you see the atomic hydrogen in this cloud or somewhere else?
So yes, we do have atomic hydrogen observations of LEO P. That's this the blue contours labeled VLA H1. So those are radio observations of the 21 centimeter transition. Basically, there are peaks in the H1 density that are close to. This is where the O star lives, right in the middle of that black clump. And then this is another area where some relatively massive stars have formed in LEO P. So the H1 does sort of coincide with the areas of recent star formation.
That's how it was discovered.
Yeah, that's right. LEO P was discovered in an H1 survey. Alpha, right? Yeah. Not too long ago. Only like a 12-year-old galaxy.
All right. Well,
All right.
Grace again.
Thanks, everyone.